So I assume my screen is visible to everyone. Is it visible to everyone? Can you see my screen? Okay, great. So today we are going to see transformer, and this PPT I have taken from Mubarak Shah lecture series, and we'll go into depth of the transformer, like what is transformer, then uh, from where it evolved, and then what are the advantages when we are using transformer. So with that, let's begin. So if you just see, transformer is being used for modeling long dependency between input sequence elements. So actually, if you just go back, uh, this transformer came around 2017, and that time, uh, and it came for the NLP task, like natural language processing tasks, so all the text-related tasks. So that time people were struggling using RNN and LSTM, and then transformer came and it has given that it has just given the it has tried to solve the problems which people were facing at that time. Okay, and that was like modeling long dependencies. So actually, you know that you have LSTM and LSTM and RNN. These are also there, but LSTM claims that I'll capture the long dependency, but still, it's not that much. It's not enough. Okay, so your transformer is giving even more. It's capturing even more long dependency. Okay, so that's the one advantages of the transformer. And the next point is it allows parallel processing of sequence, which was not there or which we were missing in the case of LSTM or RNN. So there, like that was like mostly like it was doing the sequential process, and that's why it was very slow. Okay, now transformer gives it is having the it support the parallel processing, and that's the power of this transformer. So now things can be done in a fast manner because we have the GPU, and in the case of RNN and LSTM we were not able to use the GPU in a proper manner. Then next thing is it allows processing multiple modalities. Okay, so when it came like around 2017, so that time like it was like people have used it for the NLP task only, and they have not tried another domain like image, video, uh, etc. But later, like around 2020, uh, like the reason was that there was reason why people have not tried it. The reason was like at that time already we had very good architectures, very good networks like CNN based GAN, autoencoder, variational autoencoder, a lot of different type of or maybe CNN. So CNN was powerful. CNN was doing very good. So that's why people have not tried it for images and videos. But when 2020 came, so till that time, people got like all those architecture, all those layers, whatever we have used in past, they got saturated. So then people started to think, hey, what we should use further. And then they found, hey, transformer is already there. So why not we use transformer? And then they try to like because you know that transformers like in the case of transformer the main thing is like it needs information uh, in a particular structure. So if you are giving in that structure, then transformer can accept it easily. Okay, so transformer is just like it is having the similar type of input for every type of data. So whatever data you are going to use, first goal is to convert the structure of the information uh, in the form which is acceptable by the transformer. Once you have done it, Now you can train the transformer for the particular task. So 2020, like in 2020, everyone started to use the transformer for image task. Even they started to use transformer for video task. And now in every domain, transformer started to be used. So what is this line is saying that allow processing multiple modalities. So that's why like now it's a transformer block can be used for multiple type of modality like images, videos, text, and speech. And the very interesting part is using similar processing block. And that's the beauty of the transformer. So just one type of like similar type of block, whatever you define here, the similar type of transformer block can be used for different type of modalities. You know that this is having different structure, this is having different structure, this is having different structure, this is having different structure. But when you are going to use these modalities, the first and foremost goal is you convert it in a form which is acceptable by the transformer. And once you have done it, then transformer will work on that. And that's why you can use similar block because you are converting the structure of the input into the form which is defined for the transformer. So the form this is it's like same form for every type of data set. Okay, so that's why. So since input now input would be similar in every case wherever you are using image, videos, text, and speech, in every case the input what you are going to give to the transformer that will be similar only because you have converted in that form, and that's why you can use the similar block for every type of modalities. This is the beauty of this transformer. Previously we were not able to use it because suppose you are solving image classification, then you are going to use 2D image and then applying CNN. If you're using if you're going to solve the text based problem, then what you're doing, you were using RNN, LSTM, and then RNN LSTM was taking the input in a particular shape. So every time, whenever your data is getting changed, your modality is getting changed, you need different type of architecture, different type of blocks, which is uh, which which is not required in the case of transformer. Same type of block, like similar type of block, can be used for solving different type of problems, different modality based problem. Okay. Now the next is typically pretend using pretext task on large scale unlabeled data set. So since it got popular, so they started to train this model for all larger data set, like all possible larger data set. And nowadays you can use it. You can just take the pretend model and then you start using it for your problem. Okay, it's very in a very convenient manner you can do it. Next is demonstrate excellent scalability to very large network and huge data set. So it's like very scalable. Like even if you're going with larger network, it's very scalable. Okay, and even it can support very huge data set. So very large network, very huge data set. If you have these all the things, there's no issue in the case of transformer. It supports. It's like very good, excellent scalability to these all the things. Okay. Now you know this GPT-4, Chat GPT. You everyone must have used it. So GPT-4, your Chat GPT is like again based on the GPT, and GPT is like one variant of the transformer. So it's like generative pre-trained transformer. It's like name given to this GPT, and it's like very. So that's what I'm saying. So transformer initially it start with the that paper, and later a lot of different variants came for the same. Okay, nowadays you can see a lot of different variants of the original transformer. Now I said like in vision application also people started to use. So for image based problem, video based problem, they started to use transformer around 2020. And later a lot of huge amount of papers came into the picture which have solved some type of problems related to the images, or you can say computer vision. Images or video, or you can say computer vision. Okay, so these are the vision application where already a lot of transformer based network have been used. So you can see like this is recognition task. It's very non-task like image classification, detection, action recognition, segmentation, then generative modeling, multimodal tasks like visual question answering, visual reasoning, grounding, then video processing, like activity recognition, video forecasting. Even if you go for low level vision, then we have image super resolution, image enhancement, colorization. Colorization is also a very interesting problem. So you can give black and white image and it can give you colorful image. It's just like in old days, like in past, if you see that time we had this black and white camera only. So generally, if you just see your old photos, you will be having that grayscale image that is like black and white image. So how should I convert that image into color image? So again, a lot of works have been done, and like we have the model. So just give that image to the model, and model will convert it into colorful image. This is similarly. This is also applicable for the videos. So you can give the old black and white videos and tell the model, hey, convert it into colorful video. Okay, like this color video. Okay. So even you can, so it can be done for old movies also. Like if you see Charlie Chaplin movie or maybe any old movies, that time like we had black and white videos only. So even using this model, you can also convert all those black and white movies, grayscale based movies into colorful movies. Okay. So these are like it's very important application. So okay, so this is all the things about 2D or video based problem, like image or video based problem. We have also 3D based stuff. So 3D, even nowadays we have 3D because we people are interested in the 3D because we generally see our like in our surrounding we generally our eyes are capable of seeing the 3D thing. So why not we should be having the 3D type of information even from the camera. So 3D analysis is for the 3D image. Okay, 3D information or 3D images. And if you have 3D images, again, you'll be having different type of challenges. And you can solve different type of problems. So these are the problems which are related to 3D analysis, like the point cloud classification, segmentation. Okay, so these are the applications where already transformer type of networks have been used in past. And nowadays also people are using it. Still people are using it. Okay. Then the next is natural language processing. So already I told you that transformer came for the NLP task only. So if you just see the natural language processing, we have a lot of different type of uh, transformer variants. Uh, they are having similar type of structure. So everyone is like initial transformer was came into that paper, and then later people have started to change the transformer, like make the next version of the transformer. So everyone started to use it and just modifying something for solving the particular task. Now these are the modified version or modified version of the transformer. So it's like came later after the first paper. So it's like BERT, that is bidirectional encoder representation from the transformer. This is again this is again popular architecture. Then we have GPT. You know that GPT, we have your Chat GPT is based on this GPT. So Chat GPT is like initially it was 3.5, and now we have GPT 4 also. Maybe you can 5 also. Okay. So GPT is like it is having version 1 to 4. Nowadays, maybe you could be having 5 version also, but at that time, like when these slides have made at that time, like version was up to 4. Then we have Robota, that robustly optimized BERT pre-training. So this is again one variant of the transformer. Then we have T5, that is text to text transformer. So these are like few variants of the transformer, but we have a huge amount of variants. If you just search scroll it, search it on Google, you can find it out like, hey, how a lot of different type of variants of the transformer networks are there. Okay, so with that, let us begin with transformer. Let us dive into transformer. How transformer, like what is the mechanism inside the transformer? So if you just see, transformer is, it consists encoder and decoder block. And inside each block, the main or core part is your self-attention. And then apart from self-attention, we have few more layers also, like layer normalization, feed-forward network, etc. So if you just see here, this is the diagram of the transformer. So you can see here we have encoder, we have decoder. Now, encoder is taking input, then doing something here, then applying the attention here. So it's like multi-head attention. Again, I'll go into depth, like what is the meaning of multi-head and like what's the meaning of multi-head. So these are all the things we'll cover later. And inside this multi-head attention, we have a lot of, it's like multi-heads means that means it have multiple head. And every head is like, is having the attention mechanism. And if you just see, just you open one head from here, you will see this type of structure. So Q, K, V, three things are coming, then doing something here, and finally we are getting the output. And this output we are saying, hey, this is like attention weighted output that I'm getting from here. Now, how it is happening? So what is the mathematics involved here? So that we'll cover. And finally, like whatever you are getting from the encoder side, you can see here, encoder side is doing, again, this is one block, and then this block is, this whole thing is like one block, and this block is getting, like you are going to use multiple blocks in the sequential manner. Okay, so one block, then after one block, you have another block, then another block, then another block. So in that manner, you will be having a lot of blocks. It's just like your what you have seen in the case of CNN. So we have one CNN block, then again after one CNN block, we'll be having another CNN block, another CNN block, because you know that one layer is not sufficient or one block is not sufficient. So that's why we take multiple blocks to solve some problem. Okay. So from encoder, finally, it will send the information to the decoder side, and then decoder will again will be having this multi-head attention. This again it is having also the similar type of blocks, and then it will process the things, and finally here you can get the, like you can solve the if you are solving the classification problem, then at the end whatever features you are getting, just apply the sigmoid and here and apply the sigmoid and then get the probability, find the loss, and then do the back propagation. The remaining things are same only, similar only, what we have seen before. Only this part is making this as a transformer. Okay, now let's dive into transformer. Okay, so before going to that, let us take this one example. Suppose we have given the word, given the sentence, hi, how are you? You can see here, these are the words in the given sentence. Now you have to like, you are going to solve, like you have to solve some problem. Uh, for that, this is the input. So now you are going to, suppose you are going to apply, you have to apply the transformer on this input. So first and foremost goal is to convert this into vector, because I know that we know that in this form your transformer will not accept, even your computer will not accept, because it needs this numerical values. Okay, so so that's why whatever you are going to give as an input, it should be converted into numerical values. So what we do, we give we assign one vector to one word. We already have seen this type of thing when I was covering this RNN part or LSTM part. Okay, so hi is, now hi you are giving to this. So we have the embedding layer. Embedding, the job of the embedding layer is to convert each word into the vector. Okay, so hi is given to, hi is converted into x1. how is converted into x2, r is converted into x3, and u is converted into x4. So we got four different vectors for four different words. Four different words. Yes. Now we have to. Now let's find the correlation between every two vectors. So I'm going to find the correlation between every two vectors. So correlation is very simple. Very simple formula. Take this vector, first vector, take the second vector, and find the correlation. And you know that correlation is if you have both vectors are very similar, then your correlation will be very high. If both vectors are dissimilar, then correlation will be low. Okay. And the range, it can go from -1 to 1, but let us ignore the negative part. Just focus on the positive part. Like so, what I was saying, like if you are getting 1 or close to 1, that means these two vectors are very similar. If you're getting close to 0, that means they are dissimilar. Okay. So we're just finding the correlation between every uh, every uh, every two vectors. So you can see here. So we have x1, x2, x3, x4, x1, x2, x3, x4. So not what I'm doing now what I'm going to do, I'm finding the correlation of x1 with x1, that is this, x1 with x2, that is this, x1 with x3, that is this, x1 into x4, that is this. In the similar manner, I am finding the correlation of x2 with respect to x1, x2, x3, x4. You can see here these are the values. So in this manner, I am finding the correlation of every vector with all the with every other vectors which are there in the uh, in that uh, in that set. Okay. Now, before going to this, before understanding this, like before trying to understand like what is happening here, now I'll say, hey, why we move towards this attention mechanism? Why we need attention? That's the very obvious question. Like what I'm saying that, hey, I am going to use attention here. Like I'll come to that part, like how we are getting it. But before going to that, let us understand like why we need it. So actually, attention, even in your real life, you are having your every time you're using this attention mechanism. So suppose I am teaching here, and you have to understand this concept transformer. So for that again, you have to give the attention. Otherwise, you will not be able to understand it. So you are giving. So suppose you have a lot of different works to do, but at this time, since your job is to understand this transformer, so so for that purpose, you are giving more attention to this class so that you can understand it. Like similarly, I can give you one more example. Suppose one guy is going to prepare for the ITG exam. So if he is going to prepare for the ITG exam, he knows like where he should give more attention, where he or she should give less attention. For example, he knows that in the exam, physics, chemistry, and mathematics, these are the subjects from where the questions would be asked. So for the preparation of the exam, he will give more focus on these three subjects. He's having few more subjects also because he is also attending the 12th class. But since he knows that his main job is to to uh, to crack the ITG exam, so that's why his more focus would be on that side, giving more attention, focus on those three subjects. So attention is everywhere. Whatever concept in deep learning or machine learning, whatever concept we are using, it's coming from the real life example only. So that's why attention is required. So whenever you are going to solve some problem, you need to give attention, more attention on some part, less attention on some part, and that's required. Otherwise, your job will be not your problem will be not solved in a proper manner. So then your question would be, uh, then why should I enforce it? Because model itself learn it. Model itself learn it, like where I should give more attention. Again, it was happening. Now it's like transformer came with this idea, like I'll use the self attention and like that. But this concept was already, this was already happening. Even if you're applying RNN or this CNN, there also like your model was giving some type of attention. That's why you were able to get the good results on the given data set. So when you are giving the images, like you are giving the image, so your model should understand like where I should give more focus, where I should give less focus, and how it is doing. It's doing based on the loss, because law every time loss is guiding every layer to go in a proper manner. So if you are making mistake, then it will say, hey, you are your whatever path you have chosen, it's not right. Whatever attention you are giving, that's not right. You should change your focus. You should change the ROI. You like a lot of questions. Again, it's very difficult to interpret it, but indirectly it is happening. Okay. So attention was already there. People were already using this type of concept, but transformer came with a slightly different idea, and it says, hey, I'll be explicitly using this attention mechanism. So in the past, mostly like whatever ideas you can see, like they were using this thing. Most of the papers, like most of the works, they were using this as a implicit process. Okay, implicit. So they assume that it will happen implicitly. But transformer came and it says, hey, I'll do it explicitly. So explicitly means like it will drive the equation for for doing the that attention, for getting the attention mechanism. So now come to the point where we paused. So what I was saying, that this is matrix that I am calculating, and now you know that this is correlation matrix. Now the thing is, can I see these all the correlations as attention values? That's the question. Because our job is to get the attention matrix, so that so that I'll apply, when I apply it, it will give me it will give us the attention weighted matrix. Because actually the goal is what? Your goal is to define the feature. Your goal is like you got these all the inputs. You got these all the inputs. These are the inputs. So you got these are all the inputs. But at this state, if you directly apply uh, your classifier, or like whatever problem you are solving, if you apply the particular maybe the particular layers, then what will happen, that it will not give you proper output. Why? Because yeah, these all the things are at the initial stage only. It's like already you're not refining this. Okay, so that's why in the CNN also, in RNN also, we were defining the features. We were combining, we were aggregating the information, so that at the end we'll be having very robust information. So again, so why I'm trying to tell you this thing here, because the job is to define the feature only. To refine X1, refine X2, refine X3, refine X4, but with the help of this attention mechanism. Okay. And for that, we have not reached to the attention, but what we have done, we have just computed the correlation matrix. And you know that correlation matrix is very simple. We have calculated it. Now the thing is, can I consider this correlation matrix as a attention matrix? The answer is yes. Why? Because this correlation is somehow giving me the information where I should give more focus and where I should give less focus. I'll just give you one example. just real life example. Suppose I want to, I want to select guys for my, again, just take the similar type of example. Suppose I want to select guys for my research team. So what I'll do? These are the guys x1, x2, x3, x4, and so on. These are the list of guys who are like available there. And suppose I'm going to take the information from x1. So what I'll do? I'll ask, hey, tell me this, tell me this, tell me this. I'll ask a lot of questions. And he will give the answer for every question. Now, I know that if I just go with only one guy, I'll just go with the things like I'm just asking the information of this guy from this guy only. Then what will happen? Sometimes this guy, like it may give the wrong information also. It may be biased also. I will not totally rely on this guy. I'm gonna select this. I'm gonna take the decision of about this guy, but I'm not fully relying on this guy only. So while taking the decision of this guy, I'll be also asking some questions from other guys. Okay. Now these are this is x2, x3, x4, and so on. So I ask the things from the x1, and then what I decided, like, hey, x1 has given this information. This much information I got from the x1. But again, for the x1, I'll also ask from the information from x2. I'll ask, hey, x2, what you think about x1? And again, x1 will also give some answer. I'll ask a lot of questions from the x2, but not related to x2. It's related to x1. Similarly, I'll ask from x3. Okay. So these guys could be like, suppose uh, x1 is like x2 could be like friend of x1, x3 could be again friend of x1, and like that. So I'll be having the information from different guys about x1. Now the thing is, should I give equal attention, equal weight to every guys for the decision of this, for taking the decision about x1? The answer would be no. Why no? Because if I give equal to everyone, equal weightage to everyone, then what will happen? Maybe x2 is x, like x2 could be, it's not like related to x1. It's not close to x1. So if x2 is not close to x1, then what will happen? X2 can give any arbitrary information about x1. He may give also wrong information. Even x3 can also give wrong information. So I'm going to take the decision about x1, but for that, what I'm doing, I'm taking the information from others also. But I'm not gonna give equal attention to everyone or equal weight to everyone. Instead, I'll give different weights to different people. It's just like for x1, suppose you are asking the question from the x1, then again you are asking the question from his parent. Then you are asking the information from his mother, his father, then you are his mother, then his friends, and all, like etc. Now, based on the closeness, I'll give the, I'll give the, like our focus would be accordingly. So if the person is very close to x1, we assume that that person would give very appropriate information about x1. If person is not close to x1, then in that case he could be having arbitrary answer. Arbitrary, you can get arbitrary information about x1. Okay. So I'm going to ask information about x1 from different people, but every people will be not given equal weight. Okay. So what I'll do, I'll I'll get the information from x1. Suppose I1 I got from x1, then I'll get the I2 from x2, then I3 from x2, then I4 from x2, x4, and so on. Now, what I'll do when I merge this all information, because anyway, like at the end, you have to merge this information so that you can get the information, the aggregated information of the x1, x1 dash. Okay. So now this is the one way, but I'll not go with this because here we are giving equal weight to everyone. But I know that if I go with equal weight, then again, whatever new information, whatever aggregated information I'll be getting about x1, that might not be correct, fully correct. Okay. It may be having a lot of noises. Why? Because these guys could be having a different type of relationship with x1. So if the person is very close, then I'll be having, we can get very good information. Okay. So we are seeing the closeness here. So if his father is very close, then I'll give maybe 0.9% attention to here. Maybe his mother is very close, then I'll give again 0.9. Maybe his friend, then I can give 0.7, 0.8. And accordingly, I can give different weights. And then we'll just merge these all the information, and then that will be my refined information or aggregated information. Okay. So what I said that we are seeing the closeness, how close they are, what's the relationship between them. So that closeness we are seeing here. Now, in a mathematical manner, this correlation can be also seen as a closeness. So if I say, hey, this vector is highly correlated with this vector, that means they are very similar. And if they are very similar, that means they are very close. They are having different similar type of features. Just like if x1, if x2, or like if suppose x4 is friend of x1, they are staying in the same room, then maybe and again they are having the same set of, like they are following the same set of routine, then they may be having the similar type of features. X1 and X4 will be having the similar type of features, similar type of information. They are doing the similar type of job. Suppose here they are they are attending the class. They are from the same department. So they are having a lot of similar type of information, and that's why they are close. And how we are deciding it? Mathematically, how you decide it? You have the correlation. So correlation also says the same thing, similar thing. So correlation will tell, hey, how close these two are. Sorry. So if they are very close, then you will be having values close to 1. If they are not close, then they'll be having values close to 0 or maybe in between somewhere. Now let's come to this matrix. So here you found the correlation. And now what I'm saying that, hey, I'll consider this correlation as a attention value. And it's obvious because you already have seen here, if the guys are they are very close, then I should give more attention. And you know that if they are very close, then it will be having very high correlation value, close to 1. And it's close to 1, so I can consider that as attention value. If they are very close, then I should give more attention. And the similar thing is happening in the case of correlation also. So correlation is also saying, hey, guys are very close. I'll be having very high value. And maximum value you can raise to 1. When they are not close, I'll be having values, I'll be having low values. Okay. So now these correlation values can be seen as an attention value because it is like proportional to the your attention values. So whenever correlation is high, that means you have to give more attention. Whenever your correlation is low, you have to give less attention. So that's why you can take this value as it is for the attention. Okay. So what is the job? Now job is easy. So what I said that we got the correlation matrix and now you're gonna refine every feature vector. Now you had the information from the x1. This is your x1. And now I'm going to define it. So what I'll do, I'll define this x1. I'll make the x1 dash with the help of all those vectors, all those guys. So x1, x2, x3, x4 with different attention value. Okay. So I'll say, hey, I'll x1. First, I'll go with the x1, and then for this way x1 we have weight w11. I know that x1 is vector, but before processing it, I'm multiplying this x1 with w11 because this is the attention. So whatever information you're getting from x1, then multiply this attention value. So I'm going to give only this much attention on x1 for getting the x1 dash. Then we have w12 and then x2. Then w13 x2, x3, then w14 x4. Now we just do the summation of all these, that will give you x1 dash. Now this in this x1 dash, now this is the defined information. And in the x1 dash, you have you have made this x1 dash with the help of x1, x2, x3, and x4. So this is your aggregated information of x1 or defined information of x1. And the similar type of job we were also doing in the case of RNN. So actually, you know that only one word is not sufficient. If you just go in a isolation manner for every word, that will not solve the problem. So what we were doing in the case of RNN, we were just combining the information. We were just aggregating the information of the words. So we started with hi, then combined the how and hi, then combined hi, how are, then combined hi, how are you. Here also we are doing the same. For getting the information of hi, initially it was like a standalone, like it was working in isolation. It was having just the information of hi only. But when I got x1 dash, now in the x1 dash we have the information of hi only, but now we have also incorporated the information from how are you. So now hi is containing the aggregated information of hi or the best information of hi with the help of with the help of hi, how are you, everyone. Okay. So in this way, like for every word, you will be doing this. So you are going to define every word. So this is like for the x1, then you will do for the x2. For the x2, you'll be using these all the values because these are the attention values for x2. Then for x3, you'll be using this. For x4, you will be using it. So every time for the refinement of every word, you're combining the information from every other words, but not with a equal attention. We are giving different weightage to different word. Okay. Now the things are very simple. Okay, sometimes we also normalize it so that everything will be on the same page. Again, I will come to this part later. But normalization is also very crucial factor. It's like also crucial step that we generally do so that everyone in this whole picture, everyone will come on the same page, or it will be having the we can say like normalization sometimes help you to get better information, to have a better representation. Okay, so that's why we do it, and again this part will come later, so that's why I'm leaving it for now, but we will discuss into the in details. Okay, so we have got it W matrix. And if I say you like how it is happening, now you know how it is happening. And simple formula for every, considering every matrix, the simple formula for correlation is x into xt. So your x is like the matrix where we have all those x1, x2, x3, x4. And then you will just multiplying with the transpose of that, and you will get this W matrix. The same thing that we have explained, like x1 with x1 with x1, x2 with x2, x1 with x3, x1 with x4. So this is happening in a single shot. Okay, so just x into x2. In x we have all those vectors x1, x2, x3, x4, and then we are doing it. You got this matrix. Now the next goal is refinement, and that I already have explained in the previous slide. So now again you are going to refine it. So this is your attention W matrix, and W matrix will be multiplied with the input, your x1, x2. This is x1, x2, x3, and x4. So when you do it for this vector, you got the refined vector. We have seen this. So when you multiply, like when 0.5 is given to this is given to this is given to this, and this is given to this, and then add it, that will give you first vector. Similarly, for this second vector, this will be multiplied like this will be multiplied with this will multiply with this will multiply with this will multiply with this, and then sum it, that will give you second. So now just you are defining every vector, every x vector. So it's very, very simple formula. Y equal to wxt, and that will give you the refined feature vector. Okay, so now our job is done. So we are applying the attention and things are happening. So what we have done, process was very, very simple. X into x, x into xt, that has given me the correlation, this correlation matrix, or you can say the attention matrix W. And then I multiply this W with xt, and we got this output. Now these are like attention weighted output, because you are aggregating this information based on the attention value. The job is done. What I was saying, hey, we'll apply the attention, and we have done it. Now whether we should be happy with this, the answer would be no. In this whole thing, if you just carefully see it, this is not new idea. Actually, your correlation is very old idea. And what you are doing, you are just finding the correlation. And then you are just aggregating the information with the help of the correlation. So this was already there, maybe 20, 30 years back. That time also it was there. And why your transformer became popular? Whether I can say like, hey, this is transformer, then you guys will say, hey, there is missing something here. I understand that, I can understand that this is doing applying the attention matrix and getting the refined feature. But one thing is missing here, and that's the big thing. And what is what is that component? The answer is, hey, there is no learning involved here. I said that I'll go, your transformer is part of deep learning, like it's like learning based approach. But what is learning? If you just carefully see this whole steps, everything is the fixed, everything whatever I'm applying here, that's fixed function or fixed input. Now W will say, hey, W is also not learning anything. I just doing the x into xt, finding the correlation, fixed function, and then applying it and getting the output. So there is no learning involved. And you cannot appreciate where there is no learning. Then what should I do? We should involve learning. So, okay, so we'll involve that. So far there is no learning. Whatever you have done, it's finding the attention, defining the features, but learning is not there. Then how should we involve learning? We should involve learning, and that's your transformer. So what transformer does, it has involved few fully connected layers. So if you see here, it's having X similar to here when we have seen in the case of like in the example. So we had X here. Now they have done, they have applied three fully connected layers here. This one, and this one. Now this fully connected layer is taking every fully connected is taking the input, is taking the same input, that is your X. So it's taking first fully connected layer is taking the input X and giving you K. Second fully connected layer taking the X and giving you Q. Third fully connected layer taking the X and giving you V. So we are getting three transformed matrix of the X. So origin is X only, but we are getting three transform matrix. And then what they have done, they have used first two matrices for getting the attention values. And you know that for getting the attention value, what you have to do in the original space, when I was in the original space, when I was here, x into xt, that was giving the w. Now here you have in the transform space, you have k and q. So what we'll do, I'll do kt into like q into kt. So q into kt. You can see here k is getting transpose, and then whatever I'm getting here, and then q is going as it is, and then I'm doing it, and then applying the softmax. Why softmax? Because it will give you the probability values between 0 and 1, and we know that your attention is also between 0 and 1. So how much I should give attention to the particular input vector. So if you just see here, if I just see the first part, if I apply the softmax, so this first part is for x1. I'm getting the attention of x1 with respect to other variable like x1, x2, x3, and x4. And now here we are giving the values. But before, like after getting this you were saying in this case, because here like things were normalized, and things were you were getting correlation, since we were applying that correlation formula on the normalized values, then it was giving the values, all those values between 0 and 1. And in negative part we were just ignoring because we are not interested in the negative part, because you know that correlation you can get between -1 to 1, but I'm not interested in the negative part, so I just 0 to 1. Now in this case, since these values could be anything, but at the end I want values between 0 and 1, between 0 and 1, so that's why they are applying softmax. So what is happening, for each row the values would be 0 and 1, and again these are like just probability values. Okay, so just like total sum would be 1 only. So total attention value that I have, that is 1, and I'll distribute this attention values to all these guys. I'll say, hey, you are x1, and I'm going to ask the information from the x1, so I'll give 0.5 weightage to this, maybe 0.3 to this, 0.2 to this, 0.1 to this. So that total will be 1 only. So these are like attention values from to all those input vectors with respect to x1, and that's what we are getting here. Similarly for second row, third row, and so on. So softmax we are applying for converting it into the attention values. Now the same thing we are doing here also. We are multiplying, we are finding wx into xt. Can you correlate like whether we are doing the same thing or not? We should not say same thing, but whether we are doing the similar thing or not. Yeah, we are doing the similar thing. Because if you say like k and q, these are not coming from different space. These are coming from x only. So these are the information of x only. If I say k and q, these are looking like a different representation. But in actuality, these are not different representation because the origin is x only. So from the same x, you are getting two transformed features, and then you are applying the correlation, and you are just trying to find the attention map. So we are doing the similar type of things, but not in the original space. In this case, everything was happening in the original space. Like your x was, you're applying, you're taking the x as an input. Here, you are not working on the x. Instead, you are working on the transformed version of x or feature of x. And how we are getting it? By applying fully connected. So that's why. And again, if you apply fully connected, you know that fully connected is having the parameters and you have to learn it. So you have involved the learning here. So in this case, they was not learning. Here you have involved the learning with the help of fully connected. Okay, so first part you are getting attention map, and then you know that next what you have to do, what you were doing here. We're doing this thing. Why? W into xt. So now the second part, like when you got this attention map, that is your W, similar to the W. Now W will be multiplied with the xt. Now again, since you are working on the in the feature space, so what will do? You have calculated V value, that is V. Again, V is the also transform version of X, and then you are multiplying this V with this W, and then getting the output here. And that output, again, you apply one fully connected layer, and that will give you the final self-attended feature map, which you were getting here. So similar thing we are doing here. Again, you can ask, hey, why we have used one more layer here? So they have used in their paper, but the reason I can give you, since everything here, if you see here, everything we have transformed into the feature space, and then we are doing all this like attention thing, and finally, whatever got here, whatever things we got here, now again we are projecting into the, we are trying to project into the original space. Okay, so what you do? Take it, go to the feature space, do all those attention mechanism, and again come back to the original space. It's just like it's not a proper, we can say, proper justification or explanation of this part, but somehow I tried to give you. But in actuality, you will be not reaching to the original space. It's very difficult to go back into the access space because you already have done a lot of things and already you have done a lot of transformation. So it's not that much easy. But again, for the sake of understanding or for understanding this whole concept, we generally give a lot of just lot of intuition or lot of uh, we can say hypothesis for understanding the particular concept. Okay, so this is your self-attended feature map. Now, if I just see these two things, if you just correlate the first part and with the second part, the things are very similar here. Only the thing is that we have involved few fully connected layers. And now the things are happening in the feature space. Apart from that, whatever we have done here, almost similar type of thing we are doing here. And you can see this much idea gave you the transformer. So that's why I'm saying, hey, transformer is not, it's not like very new stuff. Whatever new techniques you are seeing here, every technique generally derive from some of the old techniques. So this is also this technique is also derived from this correlation based feature refinement technique. Now what they have added, they have just added few more things so that it would be learnable. Because here it was not learnable. Now this is learnable. So you'll do a lot of things again, you'll apply and you have to go back. And once you go back, feedback, then these all the W's would be learned. They will change their values. So yeah. So again, just take the example. So suppose we have n sequences, like n words in the given sentence. So we have x1, x2, x3. Like we have converted in, we have applied the embedding and then we converted into vector. So we have x1, x2, and up to xn vector. That is your x. And so if you see like in x, what is the dimension of this matrix? So dimension of the matrix is n into d. That means we have n words, and each word is having d-dimensional vector when you have converted into embedding. And now what you are doing, you have to define this wk, wq, and wv. Now this wk will it will give you k, wq will give you q, and wv will give you v. So now we have to define the size of this. So WQ, you know that this is fully connected layer. So it will be applied at on every input separately. Okay. So let us give the dimension of this WQ. Let us see this WQ and give like this will transform D vector into DQ vector. That is your WQ. is the WQ. And WK, it will take, because every time your input vector is same only, because you have n r n into d, this one. So d is the vector, d is the size of every word. So, and we are going to apply this fully connected layer for every word separately. Okay, so that means like the input size is d, and we are going to some other size, like that. In this case, that is dq. In this case, maybe it could be dk, and wv, it could be d into dv. Okay, so this is the fully connected layer. First fully connected, second and third. You can see this wk d into dq, this rd into dk, and this rd into dv. Now what you have to do? Okay, so then what you're doing? You are projecting your x into k, q, and v. So if I write equation for this, then it will be like q equal to what? X into wq. So x is what? X is your uh, like n into d dimensional vector, and wq is what? D into dq dimensional. Like this is the matrix, n into d dimensional matrix, and this is d into dq dimensional matrix. So if you multiply these two things, it will give you n into dq dimensional matrix. So what we are doing, we are just transforming the features or the information of every vector. So now initially we had d, now we reach to the dq using this fully connected layer. So it's like you are applying the fully connected layer. Similarly for k also, you'll be having x into wk. For v also, you'll be having x into wp. So here you'll be getting n into dk. Here you'll be getting n into dv. Now you have to apply the attention that we have seen. So we reached to the k, q, and v. Now you know that here like you have, it is like you are doing find some, it's like very it's related to your correlation that you are finding here. So it's like q and into transpose of kt. So you can see here q into kt. So q is having dimension n into dq, and kt is having dimension uh, k is having dimension what? N into dk. So if I take the transpose of that, then it means kt is having dimension uh, dk into n. Now if you want to do multiplication of these two matrices, so you know that if I want to do it, then this dq should be equal to dk. So that's why whenever you are going to define it, you have to be careful by fixing the size. So your size of dq should be equal to dk. And then if you just multiply these two things, you'll get n into n dimensional matrix. And the similar thing we were getting, like because in the case of correlation also. So like it's like correlation of one vector with all other vectors. So in this way, you'll be having n entries because you have n words and you are finding the correlation with all other words. So that's like n into n dimensional. In that case, like we have four words, we will getting 4 into 4 dimensional matrix. Here you are getting n into n dimensional matrix. And then you are like we divide with this is like you're normalizing it. So we divide it root of dq, like dimension of dq. So dq is like your this. So whatever the size here, will take the under root of this and divide this whole term q into kt by this. So this is like normalization. So it's generally, if you do not do it, then maybe what can happen that your, because you know that your words if you're not focusing on the size of the vector, so your size of the vector could be vary in a great extent. So maybe your size is very large. So if your size is very large, like the vector size of the each vector is very large, then it may influence on the correlation value. So maybe if the vector which is having very large vector, that may influence on all other vectors. So that's why putting everyone on the same page, so that there should not be biasedness. There should not be our like attention value should not bias towards some vectors. So what we do, since I know that your correlation, whatever you are calculating here, this is dependent on the vector size also. Because if the vector size is very large, then there is chance of getting very higher value. If your vector size is less, then there is chance of getting lower values. Then why not we should put this and this on the same page, so that your model will be not biased towards the size of the vector. So it's very simple thing, because if you have very large vector, you'll be having a lot of multiplication value. You're doing the dot product, you're doing the multiplication with q and kt. So since you have large, it's like element wise multiplication. So if you have suppose 1,000 values, 1,000 dimensional vector, you cannot compare with 1,000 dimensional vector with 10 dimensional vector. Because 1,000 dimensional vector will be, if values are like, suppose let us assume that values are positive, then 1,000 dimensional vector will be having very large value after doing this element wise multiplication and then summing all those values, compared to this 10 dimensional vector. So actually that's why like the size is also the biasness factor. So it may create the biased, it may give you the biasness in the system. So that's why what they have done, they have normalized it by dividing the root under the size of the vector, of that query vector. Okay, so this is the normalizing factor, and after that they applied the softmax. You can see here softmax, and whatever you are getting from this part, which is getting multiplied with v. Okay, so if I see here, so if this part was giving n into n, and then if you divide with this scalar values, it will not change anything. Dimension will not change. Only the values would be changed, but dimension would be remain same. And then you are multiplying this with v. And what is the dimension of the v? The dimension of the v is n into dv. And finally, you are getting z. That is your n into dv. Okay. Just ignore this. Yeah, so we're getting it here, and then again we are applying one fully connected for getting the final feature map of this attention block, and this is called self-attended feature map. So more or less you are getting z, and this z is like attention weighted. Again, we are applying one more layer, but I'm just ignoring that part. So your z is, you are getting the z using this formula, what we have seen here in the architecture. Okay, so now I can take the one example, a simple, just take the values for the n and d. So suppose you have nine vectors, 9 words, and every vector, every word is being represented by 3-dimensional vectors. So we have x equal to 9 into 3, and then we have this uh, again we are defining this first wq of size 3 by 3, giving the this is like your fully connected layer wq. Then again wk I'm giving 3 by 3, wv I'm giving 3 by 3, and then we'll find the q, k and v. So q is 9 by 3. Like q you are going to calculate using x into wq. X is what? 9 by 3, and q have defined 3 by 3. Like you are going from same size vector to same size vector. So 9 by 3 into 3 by 3, if you multiply it, you will get the 9 by 3. Similarly for k, x is 9 by 3, this is 3 by 3, you will get 9 by 3. Similarly for v, 9 by 3, 3 by 3, you will get 9 by 3. So these are like k, q, and v you got, and then you apply the same formula. So q into kt, if you do it, so q equal to your 9 by 3, and kt will be like 3 by 9, so it will give you 9 by 9, and you divide with this root under dq. That's like 9. Dimension will be again 9 by 9 only, and then you apply the softmax. Again, it will not change the dimension; it will just change the values, and then finally you are applying v. That's like 9 by 3, And so 9 by 9 into 9 by 3, that will give you 9 by. So this is the attention weighted matrix that you are getting. So this is like your attention that you are applying. Okay, so a lot of resources are there. These are the very good resources. Like this hardware, from hardware you can like this. You can even first thing is like you can also read the paper which came in 2017, and you can see like more than 1 lakh citations are there for this paper. And again, uh, this Jalma, like it's this is very popular blog, and he has explained in a very nice manner. So you can also uh, just you can go through that for understanding this whole thing, and even you can also take the things. Even you can just you can go through this deep learning CS 886 deep learning and NLP lecture. So we have like I will just explain the main component of the transformer, but still we have a few more things to to discuss. So that we'll do in the next class. So this is your transformer. This is the main mechanism of the transformer. Now you guys could ask questions, so I'll allow you to speak and ask a question.
Hello, sir. Good morning.
Good
So,
morning.
in this PPT, you had given the example of the image in which we have RBG kind of data is there with the help of that. Like we are doing this below, sir. Last one, the PPT which we were showing, na? In this attention mechanism you were discussing, right?
Yeah,
Above
you're
one, yeah.
saying this one.
Yeah, this one. So here, first thing I want to ask, like, if there is image, then it is fine. Like, we are doing the transpose between K and Q, and then applying softmax, and we are getting the attention
Uh,
map, right? And then the third parameter, that is V, we are going to do the softmax again, right? We multiply with attention map and v, and then we are applying the one fully connected layer, and then we are getting the output.
mm,
But
mm,
as in the starting you said that transformers we are using everywhere, like this chat gpt and all, there we are just preparing the this embeddings, right? And
mm,
then doing the applying the so
mm.
in that case what all parameter means, what all two fields in which the transpose and one is the transpose, another one is without transpose we are doing, then softmax we are applying. So that is not getting clear for me, sir.
No, actually, this X is not your image. Don't confuse with image. But I said like
Okay.
X is like this X is like your sequence of words. So when I was explaining this thing, so what I told you, if you just recall the first slide of like where I started the transformer. So I told you like we have given the sequence of words, and then we are converting into the vectors. So every word is getting converted into vector. So here if you see like we have 4 words, and we have like we converted into 4 different vectors. So your n is 4 in this case. Now in the example where I was showing it to you. So here in this case we are considering n words from x1 to xn, and this just combining these whole words like in a matrix, that I'm saying as a x. So x is your this x is matrix, but it's not
Oh,
image.
okay, sir. I got it, sir. Okay.
I think you have confused with this x.
Yeah, yes, sir. Yes, sir.
This
Now I got it. Okay.
yeah. Yeah, any other question?
Yeah, so transformers, you said you'll be we can use them for image, audio,
Mm,
and text and video
mm,
classifications. Okay,
mm,
so that's a
mm.
multimodal model.
Yeah, yeah, yeah.
So here you are given example of a text classification here because you consider an
Yeah.
example of x1 to xn as a text classification. But
It's
you
not
said that
classification. It's not classification, but like we are refining the text-based information. That's all. Here, actually, one block is not doing classification. It's just defining the features. That's all. At the end, like if you take the full encoder decoder architecture, and maybe your job is classification, then at the end you have to apply the softmax layer for getting the probability
Architecture.
equation.
I need to apply the architecture at the end.
Yeah, this is just one block. Even it's not one block. It's like part of the block. It's just one. It's just like if you just correlate with the CNN. In the case of CNN, you had the filter.
Yeah.
So it's like similar to that. So it's just like one the mechanism that we are using, but this mechanism would be used multiple times while defining the transformer architecture, the big architecture.
Okay, sir. Okay, sir. Now, if I have a multi-model data like image, text, video,
Hmm.
audio, all of them
Hmm.
together, then what kind
Hmm.
of technique that you'll be advising us?
Yeah, again, I'll also cover that part, like when we'll be having
Okay,
image, then
okay,
how to convert it into the form which will be acceptable by the transformer. So we'll
okay,
do
okay.
it. I'll cover it.
Okay, for image, we will be using the respective architecture, and for text, we'll be using NLP kind of architecture, and it will be correlated to respective type of data that we are transforming here. Yeah.
Yes. Yeah. Here the block, whatever block we are defining here, this block is applicable for every type of data.
Mm.
The thing is like you have to convert whatever data you have, whatever modality you have, you have
Yeah,
to
vectors.
convert. Yeah, you have to just convert that thing into
You
the
can
shape which is acceptable here. That's all.
vectors. That's all.
Yeah, vectors. It should be converted into vector. Yeah. So that we'll see, like even if in given the image, then how to process the image, and suppose you have to do the image classification, how can we do it using this transformer? So I'll show you. I'll
Okay,
give you that example later. Maybe today only. This next class we'll see. Like I'll give you that also. If you time allows, then I'll give you. I'll cover the that part also. That's called VIT. The initial the first architecture was for the image based problem. That was VIT. We'll see that thing.
okay, sir. Okay.
Any question?
Sir, one quick question. When we started the transformer architecture, you said that the encoder decoder is the core of this transformer
Hmm,
architecture.
hmm, hmm.
Can you say the self attention is a part of the encoding process, or there are few more things to come?
Yeah, actually, when I started with this, then I've shown you the diagram here. Now you can
Yes.
see in this diagram, I have only talked about this part. So
Okay.
this
Okay.
we have multi-head, and then in this multi-head, one head, every head is doing this, and I've just discussed this part. But you can see here, this block is getting repeated n times. This is your architecture that is given in the paper. So they have used the similar type of block every time, like n number of times, in the encoder part also and in the decoder part also. And then at the end, they have solved some problem. At the end, they are doing some classification. Okay, so I have just talked one part, this part, the main component. Again, I will come few more things like these all the layers that will come later. We'll discuss each and every stuff.
Can you resemble that these whatever you explained, it's similar as a propagations, forward propagations kind of thing, right? In CNN.
Whatever I have discussed, that is just like one element of the any architecture, whatever you are going to design using this. So suppose this is the architecture. This is the architecture. Here we have full like it's solving one problem. It's like we can also say this is a network. We have
Okay.
encoder,
Yeah.
decoder, then encoder is taking the input that like X and it's converting into vector, like then giving to this block. This is your transformer block where we have multi-retention, normalization, a lot of different type of things are there. And then whatever you are getting output from this block, it's given to the next block. Again, whatever like that block will take this output of this as an input, and again it will do the similar type of things like multi-head, just like in the CNN also. Now we had, like suppose you take the example of ResNet, we had multiple residual block, and every block was applying the that block over input, that function over input, and it was giving the output. Here also we are getting the similar type of things. So this is block, and this is getting multiplied on getting applied on the X, your input, and giving you the X. dash. Again, x dash will be given to the next block of this. We'll get the x double dash and like that. Maybe we'll apply n number of times. So it depends how many block we want to. Just like it's like again trial and error. Just like in the case of CNN architecture, we were taking different number of layers. So here also you can take different number of layers. But at the same time, it will also use the it will also increase the complexity space because every block is having uh, the weights parameters. So you have to save it in the memory. And again, it is having a lot of matrix multiplication. So computationally, it's like your time and space both are getting increased. So that's why these are all the things you have to keep in your mind, and then you have to decide like how many layers I should choose, how many blocks I should choose in the particular layer, encoder layer, or maybe in the decoder layer. So we'll come to this part. Don't worry, this is a starting point, and I have somehow tried to uh, relate this thing with the correlation because this whole thing, the whole idea has been derived from the correlation only, and that's why I put time for this because once you understand it, later part is easy only. So later part will be just uh, taking the things from the previous stuff only. And even if you see in this transformer, just correlation part that we are doing explicitly, remaining things are coming from the past only. If you just see the this layer, WK and WQ, these are just fully connected layer. So we are just taking the fully connected layers here. That's all. The three fully connected layer, this is fourth fully connected layer. And then this mechanism is like making this transformer different, which was not there in the previous paper. Like they have not tried in this manner, uh, especially for the text tasks.
So,
Yes, thank you,
so,
sir.
so,
Got it, correct, sir. Yeah.
so the transformers can be applied before the fully connected layer and after the fully connected layer. It can be applied on both the side. Here you said that
Yeah,
W1, W2, W3
uh,
uh, can be applied. So they are fully connected layers.
but this whole thing you consider as a as a self-attention block only. But again, what you are saying that can be done. So even you can take the feature X, uh, maybe you can apply fully connected. You can arrange in any order. Okay, but this whole thing make this as a attention block because first you are transforming X using the fully connected layer, and then you are finding the correlation, and you are saying this as a attention map, and that attention map is getting multiplied with the input, and that's the final output that you are getting here. That's like your attention based refined output. And again, we are applying one fully connected, getting this. So this is the final output that you are seeing that is coming from one element of this self attention. So whatever, like this is the this whole thing is it will be considered as a self attention.
So that is multi-head attention. One block of multi-head
One
attention.
one block of the one head of the multi head attention.
Okay.
I'll come to that multi-head and all those things. It will be again more clear. I'll also take few more examples. Will show you like how it is happening, how the attention is happening. So don't worry, like I'll come to these all the things. But by concept wise, is it fine to everyone till now? Like what I explained, how it is happening is clear to everyone now.
Yes, sir. It's clear, sir. Means transformer is a concept which actually transforms the input into a self-attention feature maps.
Yes, so we're just applying the correlation. We're just finding the correlation,
Mm,
and we're saying that correlation as a attention map, and
mm,
then we are multiplying that attention map with the input,
mm.
and that's giving you the refined feature from the particular attention block of the transformer. That's all. The same thing what we were doing, like when I shown the example, it's not different than that. But apart from the learning, otherwise, whatever I have shown, like we have seen in this example, the same thing we are doing here. There is no any new thing which is here, but apart from the learning. So just we have so that's why like without learning there is no deep learning. So if we say hey transformer is like part of deep learning, then there should be like learning involved. and that's why they have involved this learning here. So this was, we are doing the similar type of things here also, what we have done here, but just we have added few fully connected layers so that learning will be involved. Hey, now you got it?
Yes, sir.
Sir, only one confirmation I need. Like this K, Q, and V, all these are they fully connected layers over here?
K, Q, and V you are getting from this, these fully connected. So K you are getting from WK.
Yes.
WK is your fully connected layer. WK is like weights of your fully connected layer, and that we have like seen, like we have to define it, and this is being applied on the on individual like feature vector of the X, because every feature vector is representing one word. So you are applying this. So it's just transforming the one vector, because you know that your fully connected will be applied on the vector. You have to give vector as input. So in the X you have like different vectors, and each vector is like one vector is for one word, second vector is second word. So now you are applying this fully connected layer on every word separately, and every word is getting transformed. It's getting like you're just transforming every vector using this fully connected layer. And once you have transformed this, then again you will get the transform of first, transform of second, transform, and this whole thing will make the K. Similarly for Q also, getting Q, the process is similar only. Just you are using different weights. So WK is different weights, WQ is different weights, WV is having different weights. And you are getting KQ value from these three things. And then you are finding the attention map with the help of K and Q. And then V is getting multiplied with that attention map. So we were doing the similar thing here also. So we were calculating W was being calculated by X into XT. That was the formula of the correlation. And
Yes.
then
Yes,
once
sir.
you were getting the W, then W was again getting multiplied with XT input, which was giving you the refined feature here, Y. So similar thing here also we are doing, but now we are not doing in the original space. We are doing in a transform space. So K, Q, and V, these are the representation of X only. They are coming from the X only. Okay. So, and we are using these three things for doing this. So first two things, K and Q, are being used for getting W. And then last V is getting
Yes.
multiplied with the W. That's is it clear to you, sir?
Yes, sir. Now it is
Hmm.
clear. So this softmax is a kind of a function which gives us
It's a
the
it's like activation function. So softmax
okay.
give you the probability values. So it's getting applied on each row separately. So every row, whatever, like every row is getting converted into softmax values. So now softmax will make every values here. Whatever output you are getting here, na, after doing this multiplying this two term k into q into kt, whatever matrix you are getting now, every row is getting converted into probability, like values between 0 and 1, so that it will be working as a attention. So like this is the first row, so it will be converted, like all the values will be converted into values between 0 and 1. Suppose zero point 0.5 is given to first one, then zero point 0.4 and zero point 0.1, maybe 0.05. So it will give these all the values between 0 and 1, and again it will also take care of that the sum of this should be 1, because total percentage we have 1 only, total attention we can give, that is 1 only. So we are just distributing these attention uh, to different vectors, like how much I should give to this, how much I should. The same thing we are doing here. But here we were directly getting like in this case, here we were directly getting the that, because we had the normalized input. So that's why we were getting the values between -1 and 1. And we were just below -1, we were just ignoring it. We were just making it 0. So we just, because our goal is either 0 or 1, either 0 or like it should be between 0 and 1. So that's why we were not focusing the minus part, because you know that if you find the correlation, the range would be between minus and 1, -1 and 1. But we are not interested in the negative part, so we are just interested in the positive part. So either 0 means there is no correlation, 1 means there is like highly, like both are like similar type, both are having like similar type of information. So yes, So that's why like here also this thing is doing the same thing. It's giving you the same thing. Even you can even you can also play around here. Instead of applying softmax, you can also apply sigmoid. Sigmoid can also give you
Yeah,
value between
yes,
0 and 1.
yes.
So you can
Okay,
play
okay,
around this. Okay.
okay. Thank you, sir. Yes.
Hmm. Okay. So then I'll stop here, and again we'll be having. I'll further continue in the next class. I'll continue. Thank you.